Fraser is going to introduce our speaker for today, who also gave a talk yesterday in physics.
Like many of us, Jack began life as a physicist. He got his bachelor's degree from Edinburgh University in Scotland. Then he got a master's degree in electrical engineering at MIT and a PhD in electrical engineering from Imperial College. Since then, he's become a professor of mathematics in Chicago, but that hides a lot of sins. In fact, he teaches almost everything. He has taught courses in biochemistry and theoretical biology and theoretical neuroscience, as well as a number of courses in strictly mathematics. Yesterday's talk was a melding of his work in mathematics with remarkable insights into neurobiology. He claims that at last his thesis is finished. He's been working on this problem for 40 years, and has made a remarkable discovery that the mathematics which was invented and developed for quantum field theory is ideally suited for dealing with fluctuations in nervous systems, particularly cortical noise, patterns of cortical noise, and so on. It was an extremely interesting talk, and surprisingly, those of us who don't know anything about field theory had the illusion that we learned a lot yesterday. And so I look forward to today's talk, which is quite different, which is a study of hallucinations and migraines. Jack gave the first talk that I'm aware of in Berkeley in 1981, when he first announced an incredibly simple mathematical description which could account for very many classes of common hallucinations. And I'm sure this story has gotten richer.
So when I gave this talk 25 years ago, the whole of the back 2 rows was filled with people from Telegraph Avenue. And as I showed these pictures, they kept saying, "Right on, man, we've seen all that shit." It was a very interesting experience for me. Anyway, So yesterday I talked about how to use modern statistical mechanics and field theory to characterize the spontaneous activity in the cortex, and for the first time, to develop a theory of neural dynamics that includes the effects of fluctuations and correlations. And I was able to show that, well, when I say I mean Michael Bice, my former student who's now at NIH, and Toru Ohiro was also a former student of mine who's back in Japan. Both of these were physics graduate students who I supervised, and we were able to, over the course of the last 12 years or so, master the machinery of field theory and modern statistical mechanics, and I was able to map it into neural network story. I first had a short account of this published in a NIPS volume in 1991 that just scraped into NIPS. They basically wanted to reject it. It was too formal for them, but one of the people saw something in it, and it got published. But that version was almost the version I have today, but didn't work properly. And Michael Bice's thesis, which he just finished, essentially solves the problem of making it work. So I'm now in possession of a mathematical tool for calculating the statistics of the dynamics of neural networks in a completely new way, which is not, which is generic. It's not subject to special assumptions. And it tells us that there's a non-equilibrium phase transition sitting in the nervous system when it's kicked away from the vacuum or ground state where there's very little activity going on. And that has characteristic exponents associated with it, that tell you what the power density spectrum and the correlation lengths and all kinds of things in the network. Today I'm going to, we also know that as you move away from that state, the description gets easier, and you can get by with the mean field description where you don't have to worry because the correlations essentially disappear as you move away from that state. And so 35 years ago with Hugh Wilson, I introduced a mathematical description of large-scale brain activity that did to throw away the correlations, and that's the mean field description. And it's taken me 35 years to go beyond that. But with the mean field description, which works when you drive the system strongly, or when it the critical point, the equilibrium state, the local equilibrium state becomes unstable, you get spontaneous symmetry breaking, as it's called by physicists, and patterns emerge in the cortex. So the cortex is highly generative. It can make patterns. And so Hugh Wilson and I saw some of these patterns in our early numerical simulations of neural dynamics. But it wasn't until the late 1970s that I had another terrific student, Bart Ehrmantraut, and he and I were able to apply the methods of bifurcation theory from nonlinear dynamics to characterizing the way in which the attractors that are present in neural dynamics emerge, and we gave the mathematical conditions for that. And so we were looking for an application, and I went in 1977 to a meeting organized by Hermann Haken in Germany on pattern formation and what he called synergetics, self-organized systems and stuff like that. And there was a beautiful talk there by David Sattinger, a mathematician, on fluid dynamics, on Rayleigh-Bénard fluid convection. If you heat a liquid from below, a viscous liquid, it starts to, at first it can conduct the heat, but if the temperature gradient increases, it suddenly can't conduct the heat away anymore, and it starts convecting. You get convection patterns. And if you look down on the fluid, if there's an indicator there, you see that the patterns aren't random. They're geometric. They're either periodic. All of the patterns that a convecting fluid makes in the initial stages are geometric. And it turned out that I realized I had been studying the map from the visual field to the visual cortex, and independently of Eric Schwartz had come up with the idea that there was a logarithmic transformation involved in the map from the visual field to the cortex. But Eric actually did a beautiful job on characterizing the simplicity of the map, and showed that it was in fact approximately the complex logarithm, which is a very interesting conformal map. It maps angles into angles, but it does very interesting things. And I realized if you took Rayleigh-Bénard convection patterns and subjected them to the inverse map, you would get very interesting patterns, which are in fact the images seen in a variety of hallucinations, which were very popular in the 60s and 70s around here and elsewhere. Please understand me, I'm not an advocate of the use of drugs. I think they do very nasty things to the nervous system, and I can understand why from the theory. But nonetheless, they provide an amazing amount of information that you can't get by using stimuli, external stimuli. They basically give you a kind of spectroscopy of the nervous system. They cause the nervous system to produce patterns, and by the study of those patterns you can begin to learn things about the architecture of the brain. And so my talk today is basically to summarize what we've done since then, and to show you that in fact doing this kind of science is like peeling an onion. First of all, you get a first theory, but that only does certain things, so then you have to develop more, and you get another theory, but that's incomplete too, and bit by bit you begin to get something that's useful. But it's quite clear that there are many layers to go before one can be satisfied that you have something that really works. So that's really what I want to talk about today. So let me pull up the talk and play it. So recently I've had the great fortune to work with Paul Bresloff, who's in the math department at the University of Utah, on some of these problems. And Paul is a former string theorist, who, as was Michael Bice, and also Tanya Baker. She's a physics graduate student of mine who will be graduating next Monday. So a large part of this is based on some of Tanya's recent calculations. And also Marty Golubitsky, who was a postdoc here in 1981, has been involved in it. And he told me that as a result of the talk here, he got really, for the first time, he saw that the stuff he'd been doing might have applications. So that was nice to find that out. So here's the beginnings of this story. All kinds of different routes to seeing these patterns exist. Flickering light, anesthetics, hypnagogic, or that means when you just wake up or you fall asleep. Many people report seeing vivid patterns. Near-death experience is, in my opinion, a hallucination. Entoptic means things obtained by pressing on the eyeballs, but both eyes, not single ones, but not too hard. And of course, hallucinogens. They're the main things that produce patterns. And Heinrich Kluver was a very well-known neurologist at the University of Chicago, by the way, who used to experiment on himself. In those days, the tradition among physiologists was to do the experiments on themselves. There weren't human subject committees or anything like that to worry about. And he used to take mescaline, the ingredient in peyote. And at first when he took it, apparently he lapsed into became unconscious. He overdosed. But the next time he took a smaller dose, and after the initial period of vomiting, he began to see things. And he described what he saw, and he saw tunnels and funnels and spirals and lattices, honeycombs, checkerboards, and cobwebs, all these different kinds of images, and he classified them. He called them form constants, and essentially he claimed that there are 4 different form constants to be seen in the imagery produced by hallucinogens like mescaline. And so the Oster in this first one is not George Oster at Berkeley, it's Gerald Oster, who was at the Albert Einstein College in New York, a biophysicist who died a couple of years ago. But he used to take LSD and then paint the images he saw, and eventually he sold all his paintings in New York at a gallery in the late 70s. I never got a chance to meet him and get some of the images. The middle one is Christopher Tyler's work in San Francisco on what happens if you use deep binocular pressure on both eyeballs. The fourth one is a rock carving about 1,000 years old from New Mexico. And the final one is Ron Siegel's work on with patients in a VA hospital on who see these honeycomb patterns, and they're very common sorts of patterns. In fact, this experience has been present in human history for a very long time. So if you look at one of the very earliest is this rock from Blombos Cave in southern Africa, 77 years before the present time approximately, where you can see that there's a geometric pattern carved into the rock. And similarly, 25,000 years ago in another in a cave, there's these funnel-like pattern carved into the rock again. And there's a bunch of anthropologists around now, David Lewis Williams in South Africa and Jean Clot in France and elsewhere, who believe that many of the cave paintings are hallucinatory in origin. That most cave paintings are geometric patterns, they're not animals. But they believe even the animal paintings are metaphors for a hallucinatory experience, that they're not actually representation of hunting or anything like that. So there's a lot of interest on the part of the anthropology community in this. Here's another one that I particularly like from 2000 BP. This one is, I think, is related to visual migraines, which I will say something about later in the talk. So there's a wealth of stuff like this, and so the question is, where is it being generated? So my hypothesis was very simple. Because under the action of the retinocortical map, these patterns become something very simple in visual cortex coordinates, in V1 coordinates, the most likely site for the origin of these patterns is V1. So your mind's eye is sitting in V1, so to speak. And there's a lot of data, fMRI data on imagery and like this, which some of you probably know better than I, that if you ask human subjects to image something and you ask them to inspect the details of the image, then V1 lights up. So V1 seems to be the place where you have an explicit representation of images that you can inspect. So we're interested in V1, primary visual cortex, as the site of the system. Now V1 is just the beginning of a long hierarchy of areas in the cortex that have to do with vision. Here's a famous slide from David Van Essen in a monkey, a particular, I think it was an owl monkey, with all the various areas. And it may be that other areas are involved, but it seems that there are very fast projections back from higher cortical areas to V1. So fast that for all practical purposes they're part of V1, compared to the lateral spread of excitation in V1, which is, propagates a little more slowly. Here's the brain for mathematicians and physicists, which is a little different from the way neurobiologists think of it. You might think this is just a joke, but actually this is the way to start thinking about the problem, to realize that the cortex, to a first approximation, is quite homogeneous. You move from one bit of cortex to another bit, there's no real change, first order, there's no change in the structure. The structure is what physicists say is translationally symmetric. You move from A to B in the cortex and you basically are seeing the same structure. Mathematically, that immediately tells you that the normal modes of behavior of the cortex have to be plane waves. So right off, just from knowing a little bit about the symmetry, the spatial homogeneity of the cortex, it must be able to make plane waves. And it's plane waves that you see under the inverse corticoretinal map that turn into these form constants. That's really the essence of this story. It's remarkably simple. So where does the data come from? Well, if you look at Roger Tutel's 2-deoxyglucose data on cats, you can see that if you present a stimulus in the visual field on the left side, you can see the image of that on the visual cortical surface of the cat. And you can see that there is, in fact, a topographic map. And if you look carefully at the details of that map, you can characterize it very simply as the x-coordinate in the cortex is the log of the radial coordinate in the retina, and the y-coordinate in the cortex is directly equal to the angular coordinate in the retina. That's the complex logarithm. And it has the nice property that it turns concentric circles into vertical lines in the cortex. It turns the orthogonal patterns, radial lines, into horizontal lines in the cortex. And it turns logarithmic spiral contours in the visual field into oblique lines in the cortex. So tunnels, funnels, and spirals all become stripe patterns in cortical coordinates, which correspond to plane waves, the peaks and valleys of plane waves. So where does one see in nature systems that like to make stripes? Francis Crick once made a remark that I rather liked. He said, there's something in embryology that likes to make stripes. And he was thinking, of course, of Turing's work, the mathematician Alan Turing's work on pattern-forming mechanisms. And Turing gave the beginnings of a very nice theory about how animal coat markings might be made by things called morphogens, which are substances that were diffusible in solution. And it turns out it may not actually work like that, but the theory is extremely interesting and has all kinds of ramifications. So in 1952, Turing showed that if you couple two reactions, an activator and an inhibitor, one of which was a bigger molecule than the other, so the diffusion constant for one was bigger than the other, or different than the other, that you could get stripe and spot patterns in a two-dimensional geometry. Bart Ehrmantraut and I showed in 1975 with an application of the mean field equations that Hugh Wilson and I had introduced, that you could do exactly the same thing in a neural tissue, and the analog of the diffusion constant was the space constant for the excitation and the inhibition in the network. If neurons either excite at short range and inhibit, and other neurons inhibit at longer ranges, or vice versa, then you can get the same kinds of patterns in a neural system that you can get from the Turing equations. And I have quite a few slides with lots of equations on them. If you're not comfortable with equations, just ignore them, and I will pass quickly through the mathematical details. But in case there are any mathematicians or physicists in the audience, I always include these, because it's actually a very nice story. What we do is we take the equation and then we assume that the system is sitting at a stationary equilibrium. And then we linearize about the equilibrium, and then we calculate the stability of the linear system and the modes. And, but now we can use the idea of symmetry. We know that the cortex is homogeneous. That means if I move anywhere in the cortex, I still have the same bit of tissue. And if I rotate in any direction, I still see the same structure as well. So in other words, it's got what mathematicians call Euclidean symmetry in the plane. And that immediately tells us that such a system will make plane waves when it goes unstable. And so we calculate the stability, we remove the stimulus because we're only interested in a noise-driven situation where there's internal noise in the cortex driving the system when the system is intrinsically poised on the edge of stability. Why is it poised on the edge of stability? That's because the hallucinogens act on the brainstem, the part that keeps you aroused or lets you fall asleep, as some of you are doing now. And it destabilizes the cortex. And so the resting state becomes unstable, so you get spontaneous pattern formation in the system. And so if you linearize the equation, you can calculate the eigenfunctions, and you can get the dispersion relation between the eigenvalue and the properties of the system. Mu is the strength of the coupling, W is the weight pattern and the connectivity, and F1 is the slope of the firing rate curve that describes the way the neurons reach threshold and produce spikes. And all of this tells you that the real part of the eigenvalue, as it goes from negative to positive, that means the system goes from stable to unstable, and the way it's set up, because of the structure of the weighting function, a particular wavelength is picked out by the system. And Kc is the critical wavelength at which the unstable mode appears, the first plane wave. And by putting in the numbers for the cortical anatomy, you can calculate that the human cortex, for example, should make 2 millimeter waves when it goes unstable, or 2.66 millimeter waves when it goes unstable. So if one had fMRI resolution that could pick up a 2 millimeter wavelength plane wave, then the prediction is one should see that transiently in visual cortex as people see the different kinds of patterns. No one has yet been able to resolve at that spatial resolution yet with fMRI, but if they could do it, then we would see that. Otherwise, one could open up the skull of someone hallucinating and use intrinsic signaling and things like that, but I don't think any committee on human subjects would allow that.
Would it be stationary?
No, they move around. They only last about 50 milliseconds. You get a vast, lots of these patterns occur. And the whole thing takes about 30 minutes or so, and then it's as if the disturbance moves forward in the head, and people began to have out-of-body experiences and emotional experiences, trips and all sorts of stuff. And those we can't handle with the mathematics, but what we can handle is this geometry that people see, because that's telling us that there's a geometry in the cortex itself. And so we can actually do this picture, Edgar Knobloch will recognize This is a picture about Rayleigh-Bénard fluid convection from Fritz Busse's work, in which the parallel is very strong between the behavior of convecting fluids and the properties of our networks. When the firing rate function for the network has odd symmetry about an inflection point, about the threshold, you get stripes being formed, but when it doesn't have odd symmetry, you get the analog of hexagons, which are blob patterns. So the cortex can make stripes or blobs depending upon the symmetry is in the problem. Everything is controlled by symmetry. This is what is so nice about this theory of pattern formation. The symmetry is very, very important. So basically what Bard Ehrmantraut and I were able to show then is that some of the form constants that Cleaver described can be accounted for in terms of very simple model. The cortex likes to make plane waves, and those plane waves turn into tunnels, funnels, and spirals under the action of the retinocortical map. That was model 1. But we know that it can't account for the other form constants, the honeycomb structures and the cobweb structures and stuff like that. And also we're treating the cortex as if it were just a retina, and we know that's not the case. Ever since Hubel and Wiesel discovered the orientation tuning of cortical neurons in visual cortex, it's clear that our theory was completely inadequate to deal with the realities of what this structure is like. And if we want to learn about the structure by using this kind of approach, we have to build into the models much more details. So the next model, so here's just to point out that here are the Hubel-Wiesel first slides indicating that the cortex has cells which are tuned for the orientation of a bar as it moves over the receptive field of the neuron, and also that these orientation preferences are effectively periodic in the cortex. And of course nowadays you do the experiments where you look at a cat and you have a voltage sensitive dye or not in the cortex, and you can see the activity triggered by different kinds of stimuli at different orientations, and actually produce maps of the orientation preference distribution in a patch of cortex, which is a lot more complicated than Hubel and Wiesel originally thought. So Hubel and Wiesel came up with the so-called ice cube model, that there were slabs of cells preferring a given orientation arranged in a linear order in the cortex, but we now know that's not true. The system is much more random than that. It's much more disordered. I wouldn't say random, but it's got a lot more disorder in it. And so Gary Blaisdell was the first person to use voltage-sensitive dyes to produce an optical image of the orientation map. This is about 4 millimeters by 5 millimeters of cat cortex. And he found that there's a patchy distribution of the preferences, but it's approximately periodic. And in a cat, the spacing's about 300 microns. In monkeys, it's about 500 microns to a millimeter. In humans, it's about 1 1/3 millimeters. And then people combined optical imaging with neuroanatomical techniques. So Ulf Eisel showed that if you injected a tracer into some neurons in a patch of cortex, by and large, the white star is where the tracer is injected, the white cell is the cell body, and the black stuff is all the axons that make connections elsewhere. And roughly speaking, they show that the connectivity is, everything basically connects to everything else in its neighborhood. It's essentially isotropic. So that's consistent with the original assumptions that I made with Bard Ehrmantraut. But then Gary Blaisdell and earlier David Fitzpatrick and his group showed in tree shrews and owl monkeys that if you looked at longer ranges, there was an interesting set of patchy long-range connections also in the cortex. But those patchy long-range connections were not isotropic. They were anisotropic. And in fact, they had an axis a main axis that was parallel to the orient preference of the patch in the visual field. So there's a very interesting new symmetry in there that I realized. So here's what the connectivity of the cortex based on that data looks like. Locally, things connect to each other in an isotropic fashion, but at long range, they only connect to patches signaling the similar orientation. So that means if you want to go from the green pattern to the red pattern, you have to first of all rotate in the direction in the cortex, but then you have to shift the label from red to green, or vice versa. So that's called a shift-twist symmetry. And so the action, mathematically, it turns out that's a new action for the Euclidean group in the plane, and it has all kinds of interesting consequences. It turned out there was one example in fluid dynamics of people studying fluids with that kind of symmetry in it. And the bifurcation story for that is very interesting. So anyway, in 2001, I worked with two math graduate students, Peter Thomas and Matthew Wiener, and with Paul Bresloff and Marty Golubitsky. And what I did was I introduced the orientation preference label as a coordinate for the system. I sort of made it like general relativity, building in the effect of gravity as a coordinate, something that changes space. I changed the space in which the cortex lives by the orientation preference, and built in the shift-twist symmetry by adding the lateral connections as a perturbation of the local connections. So now you might not recognize this, but this is a situation very, very common in quantum mechanics, where you have potentials that are perturbations of a potential that you can calculate properties of, but now you have something that's a little bit different, and you have to solve that by perturbing off the solutions for the case that you can calculate. That's called Rayleigh-Schrödinger perturbation theory. And so what we did, I won't go through all the details, but we essentially applied the same methods to this calculation that you do in calculating in physics what's called a weak field Zeeman effect. If you have atoms in a magnetic field, they show the spectrum, the emission spectrum of atoms changes because of the effect of the magnetic field, and it's exactly the same in this calculation. What is going on is that without the long-range connections, you can get plane waves at any phase. So you get mixtures that are all mixed up. There's no defined phase, no pattern, because you've got a linear combination of plane waves. As soon as you add the lateral connections, you remove the degeneracy, and now you get either sine phase or cosine phases. So the whole thing simplifies. And so we were able to, I realize this is a little technical, but this is the outshot. We were able to show that the two kinds of patterns that you got, sine waves or cosine waves, combined in a two-dimensional geometry into different kinds of cortical patterns, and under the action of the visual field, the even eigenfunctions gave exactly the other form constants. And then Marty Golubitsky and Schaefer had proved a theorem which is very interesting. It's called the equivariant branching lemma. Why they call it a lemma, I'm not clear. It says the following: if you have a dynamical system with a symmetry associated with it, so that the resting state has a particular symmetry, like Euclidean symmetry in the plane, and it goes unstable, there exists a branch of solutions for that system which has lower symmetry. The solutions have lower symmetry than the initial state. That's called the broken symmetry. And what they proved was that the symmetries that emerge in the new solutions are subgroups, certain kinds of subgroups of the symmetry group before the change. And so we calculated what these subgroups were and what patterns should emerge, and we found there are only 4 kinds of subgroups. And they correspond exactly to the form constants of the Kleber classification. So we found what we think is an absolutely beautiful result, because it's basically independent of data. And I'm a theorist who likes to think that the equations should drive the results, not the data. I was once, my colleague in physics in Chicago, my late colleague Chandra Sekhar, on the occasion of his Nobel Prize for work he had done 51 years earlier. He always used to complain bitterly about it to me, that he had to wait so long. He gave a rehearsal of his Nobel Prize talk. It was about stellar evolution. And another distinguished physicist in the audience, Jim Cronin, said to him gently, he said, "You know, Chandra, some of these predictions of yours could be tested experimentally. We now have ways of measuring these things." And Chandra said, "Oh, but the conclusions follow so beautifully from the assumptions by the mathematics that they don't need to be tested." So I feel this is the same deal. However, there's not just orientation in cortical feature maps. There's spatial frequency, there's color, there's binocular disparity, there's directional selectivity. So what I'm going to show you now is that we basically came up with a way to incorporate all of these things into the story. It's not finished yet, but I can show you the path, and it's clear that it will work. So let me show you what we did. So take, for example, spatial frequency tuning. Cells in the cortex are also tuned for spatial frequencies. And there's a map there. It's not as clean as the map for orientation preference, but there is a map there. And it turns out that two groups, one in San Francisco, Mike Stryker's group on the right, Noam Issa is now at Chicago, but he was a graduate student of Mike's. And the Bonhoeffer group earlier in 1955 showed that if you presented low spatial frequency gratings and also high spatial frequency gratings and did optical imaging, you found that the regions of low spatial frequency preference seemed to surround about half the singularities of the orientation map. And by inference, the other singularities must be regions of high spatial frequency tuning. And Stryker and Issa actually confirmed that in cats. So what this means, this led Paul Bresloff and I to come up with an extension of our ring model for orientation tuning to include spatial frequency tuning, and we put it on the surface of a sphere. So the coordinates for orientation are run around the sphere, around the equator, for example, you can see that, whereas the coordinates for spatial frequency tuning run from the poles up, and you have to compress spatial frequency, which is not a periodic quantity, onto a finite strip. And we found a way to do that, and then again I built into the story the spatial frequency preference as a coordinate. And so instead of rings, we got spheres. Now what does that mean? Now mathematically, what are the eigenfunctions associated with a ring? They're just sines and cosines. What are the eigenfunctions associated with a sphere? They're spherical harmonics. So we built the solutions to the pattern forming problem out of spherical harmonics. And it works, and you get new hallucinations now. Now you get hallucinations with contours, but they can have different widths. So you get a new family of form constants out of there, some of which look remarkably like the other two form constants which the ring model didn't actually account for. So it looks like this theory works very nicely for orientation and spatial frequency, which after all are the two components of two-dimensional spatial frequency tuning. But the problem is that there are also all kinds of other maps now. There's direction preferences, there's disparity in direction maps in MT, there's direction maps in V2, area 18, and then there's color maps in V1 and V2, which are a bit disordered, but they're there. So how to build the theory to include all these other things? So the first thing I tried was to go from a sphere in 3 dimensions, the surface of which is 2-dimensional, to imagine a sphere in 4 or 5 or 6 dimensions with a lower dimensional surface. The harmonics of that are what are called hyperspherical harmonics. And I thought, well, we can build a solution out of hyperspherical harmonics. But it doesn't work because there are far too many singularities in these hyperspheres that have no counterpart in data. So I really am driven by data. I was only kidding. So then the question is, how do we go incorporate these things? And the answer was that we went back. Let me just pass over the story. We went back to the original model. We didn't include the features labels as coordinates in the story, and so we went back to a flat Euclidean geometry, not a curved geometry, but a Euclidean geometry. It's like going back to a Newtonian view of the world rather than an Einsteinian view. And then we added the feature map only as a perturbation of the lateral patchy connections, because that's the only thing that connects the different feature patches together. And we also took advantage of an idea that had emerged from Paul and I's thinking about these problems. If the structure is periodic, which it seems to be, approximately periodic, then it's basically like a crystal. So we wrote a paper entitled "The Visual Cortex as a Crystal." And that led Paul to realize that, well, if we really take it seriously that the cortex is a crystal, the eigenfunctions, the normal modes of behavior there, are what are called Bloch waves, well studied in crystals. So we used the techniques of crystal physics to start thinking about how the cortex is organized. And so this is quite complicated now, but basically, let me say explain the idea. Don't worry about the formulas. What we're saying is that the feature maps can be thought of as a crystalline lattice. And now we're going to produce the Turing-like mechanism that spontaneously makes patterns. These patterns have a certain wavelength. The lattice has a certain wavelength too, a spacing. If the two are commensurate, the Turing patterns will fit into the lattice and be organized by the lattice. They will be pinned to the lattice. If they're not commensurate, they're independent. The two things are independent. It's the spatial analog of locking in oscillators or entrainment phenomena. And so what we did was to show that, in fact, that's exactly what happens. And let me go over the ocular dominance thing. And so you can see it if you look at the Fourier transforms of the weighting functions. The Mexican hat Fourier transform in the center, that's the local weighting function, the one that drives the Turing instability. And the other Fourier transform is the crystal lattice of the iso-orientation patches. If the two of them fit together and are commensurate, as shown in the right-hand side, then you get essentially a near resonance condition, and the lattice pins the pattern. And in fact, if there's more than one solution to the problem, you get regions where the phase changes again. There's disorder, and those are described in terms of what is called the Sine-Gordon equation, the solutions of which are solitons. And you get these transitions between different regions where you've got things pinned to one lattice structure, to one orientation. You have some disorder, and then they're pinned to another lattice orientation, and so on. And so we were able to make use of this. So here is Tanya Baker's simulations of this kind of situation. Here you have beta equals 0. That means the patchy connections are 0. So now you get no pinning, and if you have noise driving the system, you get a plane wave forming randomly, and then you get another one forming. They have random phases, so you don't get you get a mess out of it. As soon as you turn on even a weak lateral connections of order epsilon squared, you immediately get pinning. And this is the one-dimensional case where you just have one orientation in the lattice. Now you go to, and it takes time. It's just like the Turing mechanism. The noise, if the noise is weak, it takes a while before the system destabilizes, and then it turns on. You do the thing with two orientations, and now you get pinning on the left to one region, and then there's a disordered region where the phase changes again. That's where the soliton is. So you get a dislocation, and then it pins again, and so on. Now, interestingly, if you do that for 3 orientation preferences, you get perfect pinning without any solitons in it, and we don't understand that yet. Francis Crick, I keep quoting, I said this yesterday too. Francis Crick once said to me that no theory should fit all the facts because not all the facts are right. And I've always liked that. But Francis one time said, he never said that, it was Jim Watson who said it. But that can't be right because I never had a conversation along those lines with Jim Watson. So if you do this in 2 dimensions, here is the Turing-like mechanism at work without any pinning. It starts to make stripe-like things, but there's also some blob stuff in there. It's a bit noisy. But as soon as you have a lattice there, the lattice pins the structure and you get a much more regular pattern out of it. And if you set up, but the relevant situation for the neural case is spot pattern formation rather than stripe pattern formation. So imagine you're forming little spot regions signaling a particular orientation. And here's what happens if you have the lateral connections. They pin it. So, but that's for a single orientation preference. Now you can pin it for 2 orientations. And again, you get this competition between the 2 and some soliton regions. And here's a simulation. We should have put in a counter because it's actually running. But you won't see it. It takes time before it actually works. But it's going to work. If we had a faster computer, of course, it would work faster. It's a MATLAB program, so it's not. There we go. And as the lighter regions are the activity growing, and it starts to pin. And you can see some places it pins to the blue ones and other to the red, and there's a region where there's an alternation. That's exactly what you should expect in these. So this is just like crystal physics, basically. The pinning in a periodic potential, and that's what it is. So the patchy connections in the cortex act like a periodic potential in quantum mechanics. And you can do this with 3 ocular dominance regions, and then it gets a little more complicated. Here's the 2D simulation where you have 3. And this is as far as we can go with the periodic idea because it's well known you cannot tile the plane with more than 3 vectors in a periodic fashion. But there have been very interesting developments in the last 20 years in crystal physics, starting from Roger Penrose's work on tilings of the plane. He showed that you could actually get what is called quasi-periodic tilings of the plane, but claimed it required non-local rules, but that's wrong. Turns out if you modify slightly the definition of a tile and allow overlaps, Paul Steinhardt and a bunch of physicists showed that you could get local rules that would do this. And basically they showed that there do exist in nature quasi-crystals. They have Fourier transform, so they actually are almost periodic structures, but they're not really periodic. And if you take a random number of vectors, like 20 or 18 vectors, and allow the Steinhardt annealing process to work, it finds itself a quasi-periodic structure where there's a local point symmetry, 18-fold symmetry, but it's approximately periodic over the plane. And I believe that's what the visual cortex really is like. And so we're actually doing the calculation at the moment to show that the visual cortex can be thought of as a quasi-crystal and that you can get basically exactly the kinds of hallucinatory images from it that people actually report seeing. So I'm almost done now. I just want to show you that if you take the patterns that in the cortex, these pinned patterns, and map them back to the visual field, you begin to see the kinds of hallucinations again. So this is a much better way to think about what might be happening than the ring model earlier, but it's basically redoing what the ring model did. And there's an arbitrary phase in the thing, so you can actually get all kinds of patterns. And let me just take another 5 minutes and then I'll done, because we actually looked at data. So Gary Blaisdell's map of the orientation preferences, we said, well, let's take that bit of data and treat it as if treat it with our methods. So we discretized it, and then from it, we calculated what the long-range connectivity would like, the connectivity between the patches. And then we used that to organize a two-dimensional simulation. Here it is with no long-range effects working, with absorbing boundary conditions. And here, and we found we got patchiness forming in certain ways. When we mapped that patchiness, we looked at that. We found that most of the time the thing was lining up with 120-degree orientation in the visual field. So here's what happens. When beta is nothing, there's no organization of this structure. It looks kind of random, except there's some zigzags in it. When beta is small and turned on, the thing starts to organize. So the patchy connections in the data can indeed organize this pattern forming process. Now what's interesting about the beta equals 0 case is that if you look very carefully at visual migraines, this is a famous picture from Gowland in 1908. He was reading when all of a sudden he began to get scotoma that propagated, and he found, they described the famous fortification illusion. I had a colleague in Germany, Bernd Hassenstein, who every month had a visual migraine and no headache. And he measured for me the position of the leading edge as a function of time. And that's the data, the raw data, 24 minutes to get from 0 to 60 degrees visual angle. And when you convert that from visual field to retinal coordinates, it's a straight line with a slope of 1.5 millimeters per minute. So if you go back to the picture, the beta equals 0 picture, and imagine you illuminate that with a flashlight at 1.5 millimeters per minute. As you move across it, you'll see something that looks remarkably like the fortification patterns in the visual field. So anyway, I believe one can account for this. Now, I actually have the rest of the story. I'm afraid I've run out of time, but basically I have a way of using the pinning story to do disparity, directional motion, and color in exactly the same way. And the next time I come here, I'll have movies of people seeing themselves falling down tunnels with light at the end of it, with rotating and zooming back and forward, changing color and flashing and moving and everything. I'll have the whole psychedelic works that people report seeing. Thanks very much. Yeah.
You're going to get someone to design the poster for you?
Well, I don't need to. I can use the mathematics to make the poster.
Did you try to go to a second Brillouin zone to see when the dispersion changes its sign?
We haven't done that yet, but that's a very good thing. We just looked at the first Brillouin zone and played with it, but I mean, we basically have all sorts of things to do. There's 100 different projects to do now.
But when you did this analysis, did you do it like in the beginning of the Brillouin, or the first Brillouin zone, or you also like try to go further up?
No, we just used the first Brillouin zone.
Yeah.
We just used it. I mean, it's complicated stuff. It takes quite a while to do the translation from the physics of crystals into this story. But I believe this is a good way to analyze the structure of the cortex. It's a highly regular structure. Now, yesterday, I guess I created a bit of a misimpression by saying that I can describe the neural dynamics as a Markov process. I wasn't implying that I thought it was a random network. It's still a Markov process, even this kind of thing. It's simply a process where the current state depends on the previous state. That's a Markov process. And the statistical mechanics of Markov processes doesn't require the system to be random. You can do statistical mechanics without having randomness. And a lot of people don't seem to understand that. And so it's true, you have to build more and more structure into these models of the cortex. But here you can get a lot of mileage by putting in very simple ideas. Well, maybe they're not so simple now, but basically you can account for all these patterns with a very simple theory. The key idea is that the cortex has a regular structure, it's got a geometric structure to it, and because of that geometric structure, it can only make a certain set of patterns, and those are the patterns that everybody sees and has been seeing for 75,000 years. Tony?
So I'm wondering a bit about the dynamics of the patterns. Would that proceed in such a way that would make you think there was a dynamical effect in the delta range? Like 1 to 4 Hz? Could it be like, deep sleep that's breaking through during the...
Yeah, I mean, there's all kinds of interesting questions that we haven't pursued yet. I mean, the actual neural model has been trivial, basically. It doesn't have proper structure in the time domain. As soon as we start to put that into the story, we'll start seeing all kinds of things that may be relevant. I mean, at the moment, I don't think you were there yesterday, but what I showed basically is that the resting activity of cortex should, close to the phase transition, should have a 1 over F spectrum. And it does, actually. There's data from all kinds of labs. What we didn't put into the model was enough temporal structure to produce any peaks sitting on top of the 1 over F spectrum. So we don't have a theory yet that has a place for a 10 hertz or a 20 or a 40 hertz or an 80 hertz peak in the system, but it's very straightforward to put it in. But my philosophy is to try the simplest possible non-trivial model first, before I start putting more details in and making it harder to calculate anything.
So what is your pharmacological theory, though?
The pharmacological theory is that noradrenaline and serotonin, etc., the monoamines, control the excitability of the cortex, and the hallucinogens interfere with the action of such drugs, and therefore destabilize the cortex, change the Sodic-Sednovsky balance condition, which is an integral part of our phase transition story, by the way.
So that could be a brainstem control?
Yes.
Right.
Yeah.
What are the implications of your theory to computation? I mean, for example, how do these symmetries, how could they actually help to form invariant features? Or did you think about connections?
Well, I mean, McCulloch and Pitts, my teachers at MIT, wrote a famous paper entitled How We Know Universals, in which they tried to do some of that stuff. But, I mean, there's just a finite amount of time to work, and I just haven't had time to think about problems. I'd love to work on problems like that, but I mean, I don't have time, but maybe somebody would. Stanley.
It seems to me there's a very beautiful experiment that your lattice inspires, that if there is a lattice of, say, 1.3 millimeters roughly spacing, in human vision, one can do a fine-grained spatial frequency tuning.
Well, Christopher Tyler did a very interesting experiment some years ago that I always cite. What he did was he let people look at a high-contrast sine wave grating, and he noticed that if he picked a certain spatial frequency, then when people looked away and looked at a noise pattern, they saw a moire after effect from looking at the grating. And he calculated what the spacing was needed, what it corresponded to and it was 17 cycles per degree of visual degree of visual angle at the fovea, and that corresponds exactly to this hypercolumn spacing that is the wavelength of these plane waves. So there indeed is a resonance in human vision associated with the hypercolumn spacing.
Okay. See, something like that, foveal vision, of course, the scaling changes
A bit, yeah,
dramatically,
yeah.
But in peripheral vision,
Yeah.
You might be able to get more homogeneous.
Right, that's right.
And change and see.
That's right.
I mean, that would be totally wild if that could be validated.
Right,
As kind of moire or just oscillation, like in contrast discrimination or just contrast detection,
Right.
Where you're in phase with the lattice.
Right, and some of Don Mackay's experiments, I think, might be interpretable in this direction as well. Some of these after effects that you see with these high contrast patterns.
Is it hard to convert a grid of neurons representing 4 or 5 different features into a two-dimensional image? And how would you do so?
A grid of neurons representing 4 or 5 different.
So you showed a lot of pictures of neural activity in a grid representing many different features. Is it hard to go from that to the image?
Well, what we do is we use, if you look at the logarithmic map, what you have to realize, you have to take the gradient of that map, that's called the tangent map, and apply the tangent map to do the calculation, but it works. But you have to be careful how you do it, but it does work. It's not hard. You can map back and forth between visual field coordinates and cortical coordinates for any of these things.
But do you use as your unit on this grid, do you use the hypercolumn or individual neurons tuned for different orientations?
Well, so the lattice spacing is basically the distance between orientation patches of different orientation. So D0 is say approximately 1/18 of 1.33 millimeters. So it's basically the spacing is determined by the orientation preference patches. So we're treating each patch as a unit. That's what we're doing.
One more question.
In other presentation, not yours, in birthday, I heard that if you look at some pictures, the noise in the brain, will make the thing rotate and stuff like that, or you see radial patterns. But if you drink alcohol, you don't see that because the noise is, so can you relate?
Well, alcohol isn't a hallucinogen. It doesn't seem to produce these patterns. On the other hand,
No, it's the opposite effect I'm talking about. It's opposite to what you're saying. Like, if you don't have alcohol, you see the patterns move due to the noise in the brain cells.
yeah, well, I mean, one thing I've heard, people have said to me that the odd symmetry patterns, the odd eigenfunctions, the ones on the right here, people have said to me that some of these patterns they have seen after taking large amounts of alcohol. The delirium tremens of alcoholic people report seeing the far right pattern
Well,
quite
with that
often.
happy note. Thank you again.
I'm sorry I overran.